Okay, let's continue our discussion. So in the last video, we have solved what will be the potential energy for such an arrangement where four spheres are placed at the four vertices of a square. So we obtain potential energy of the system here. Now there is another part. We have to obtain potential at the center of the square. So we have already discussed about potential energy and potential. So what will be the potential at this point here? So let's bring a test mass here. So here we have a test mass. Let's say we have brought a test mass here, m prime. So if we brought this test mass here, it will experience four different gravitational fields due to these four spheres. And I'm talking about this test mass only, not about the complete system. So if it has been brought here, there will be change in potential energy, and this test mass will experience a potential energy this much due to each sphere, and there are four such spheres, so we can write into 4, or simply we can write minus 4 g m prime by r, where r is the distance between the centers of the test mass and each sphere. These all distances are same. Okay, so and what is the r in terms of L? So r can be written as, look, diagonal is L root 2. So R can be written as L root 2 divided by 2, because this is half of the diagonal, and we can write L divided by root 2, and we can replace this value here. So we will get minus 4 G m prime and L by root 2, or simply minus 4 root 2 G m prime by L. Now, this is potential energy for this m prime here. So we can get what will be the potential at this point. And potential we have already defined. It is potential energy per unit mass. And here we have test mass. So we can write minus 4 root 2 G m divided by L. This is the potential at the center of this arrangement. Okay, let's move to the next topic, escape speed. So what happens when we throw a stone from the earth's surface? We all know that it goes up to certain height, and after that it returns to the surface. So now there is a question: is there any speed with which this stone can be thrown so that it never returns? So the answer is yes, and that minimum speed required to escape from the earth's gravitational influence, that speed we call escape speed. So loosely we used to say escape velocity also. So let's derive the expression for the same, and here we are going to apply conservation of energy. So let's say this stone has been thrown so that it attains some distance where the earth's gravitational influence is zero, or you can say gravitational potential is zero. And let's say at this point this stone comes to rest, so the kinetic energy at this point is also zero. Now if this stone is at a distance of r, so let's say this stone is at a distance of r from the earth's surface, from the center of the earth, not the surface. So if this distance is r, it has potential energy of minus g and mass of the earth, and let's say it has mass small m, so divided by r. Now at this position, if we are imparting some velocity, so that velocity will give rise to kinetic energy, and kinetic energy can be written as 1 by 2 m v square. Let's say we have thrown it with a velocity of v. Now at this point and at this point, the total mechanical energy should remain equal. Why I am saying that? Because once it has been thrown, the only system is the earth and this particle or a stone or body, whatever it is. So in this case, the total mechanical energy, let's say E, at this point should be equal to the total mechanical energy at this point, let's say. So at this point, we have said that potential energy is zero, so that there is no influence of the gravitational field of the earth, and kinetic energy is zero, means the particle or the body is just reaching this point. So at this point also, the total mechanical energy should be 0 only. And the total mechanical energy at this, let's say this is point A and this is point B. So at point A, total mechanical energy is minus G m into m by r, which is potential energy, plus 1 by 2 m v square, and it should be 0. Now, 1 by 2 m v square equals to G m m by r, or we can say uh, v square equals to 2 G m by r, or we can say v equals to 2 G m by r and the square root of this thing. Now, this is the minimum required velocity so that this body can escape from the influence of the gravitational influence of the earth, and this velocity we call, or this speed we call, escape speed. Now let me further write, we can just write this thing 2 G m by re, if we are saying that this point is at the surface, on the surface of the earth. So if we are taking the minimum speed required from the surface of the earth, then this r will be the radius of the earth, re, let's say, and then we can write it under root 2 G m by re square into r. I have just multiplied and divided by re. Okay, now we have 2g. This is acceleration due to gravity. We have obtained already re. So in simple way, we have the minimum speed required, or we can say the escape speed is under root 2 into acceleration due to gravity into re. This is the expression for escape speed. Now we can generalize the thing, and we can use the same expression for other bodies too. Like, take example in case of moon. So what we need to do only, escape speed from moon, or moon's surface more precisely, this will be under root 2 gravitational acceleration due to gravity on moon and moon's surface precisely, and radius of moon here. So this is, if we want to know what is the escape speed from the moon surface, this is from the earth surface, and this is a generalized thing, means you can obtain from any position, not especially from the surface, but depending on the position you can use r, and you can say what will be the escape speed from a certain height from the earth surface. You can use this thing, and here r is nothing but, you can see clearly, if we are taking this height from the surface is s, so this small r is h plus radius of the earth. This is what. So, and if we are taking h to be 0, that is, the body is being thrown from the surface of the earth, then we have to use, instead of this r, we have to use re here, what we have done already. Okay. And if you calculate these things, you are going to get this escape speed is nearly 11.2 kilometer per second in case of earth. And in case of moon, you can calculate with the data, and I guess it is going to be something 2.3 kilometer per second. So only thing you need to know that what is the uh, mass of the moon and what is the radius of the moon, so that you can come to this expression and you can solve it for escape speed. Okay. Now let's take an example here, and then we will end this video. Okay. So here we have example 7.4. Two uniform solid spheres of equal radii r, but mass m and 4m, have a center to center separation 6r, as shown in figure 7.10. So this is the figure. Let me redraw it a little bigger. Okay. So here we have two spheres, and these spheres, let's say it has mass m, and this sphere has mass 4m, and radius, let's say it has r, and the radius of this sphere is also r. Now, what is the question? A projectile of mass m is projected from the surface of the sphere of mass m, here we have a small m, here capital M, directly towards the center of the second sphere, obtain an expression for the minimum speed of the projectile so that it reaches the surface of the second sphere. Okay, so we have to obtain the escape speed in this case. So we have two spheres here. So if there is a projectile, it will experience two different potential field here, gravitational potential field. So let's say here we have a projectile of mass small m and it has been thrown. So if this projectile has been thrown, it will move to this surface, to the surface of this second sphere. But there is a catch here. This projectile is experiencing two different forces which are opposite to each other. So if you see, let's say the projectile is here at this point, and at this point, this projectile is experiencing one gravitational pull due to this 4m sphere and another just opposite due to this m mass sphere. Okay, so there will be a neutral point where these two forces, let's say this is due to, let's say this is first sphere and this is second. So due to this sphere and due to this sphere, these two forces will be equal in magnitude. There will be a point, or we can say there will be a neutral point here. So let's say this is O1 and this is center of second sphere O2. Okay, so we can find out what is the distance of this neutral point. So in the question we have given that center to center distance is 6r. So let's say from here, from the first sphere, this neutral point is at a distance of r. So from the second sphere center, it will be at a distance of 6r minus r. This is what. Now, if this is neutral point, these two gravitational forces should be equal in magnitude. These two gravitational forces should be equal in magnitude here. So we can write G m by, look, from here to here it is r. So we can write r square equals to G, it has mass 4m. So we have to write 4m m by, this is 6 minus r, 6 r minus r square. Now we have 1 by r square equals to 4 by 6r minus r square. So from here we can write 6r minus r whole square equals to 4r square, or we can write 6r minus r equals to plus minus 2r. Now we will get r equals to 1. When we are taking this is as plus 2r, we will have r equals to 2 capital R, and when we get it as minus 2r, we will have r equals to minus 6r. So this is not useful here for us. It may be a glitch in the matrix, but okay. So we are dropping this thing here, and this is what we are going to accept, as we have distance here and this should be positive one. So from here to here, this distance is 2r. So now we have obtained the neutral point from the center of the first sphere. Further, we can continue our discussion, and now we have to obtain, let me get back to the question again. So a projectile of mass m is projected from the surface of the sphere of mass m. Okay, so this projectile has been projected from here. Let's say this point is a and it has been projected to the surface of the second sphere. Let's say this point is b. Now we have to obtain what should be the minimum speed with which it has been thrown from here. Let's say this speed is v. So the minimum speed here we have to obtain so that it can reach up to this neutral point. Because after this neutral point, this F2 will be dominating. The gravitational force due to this second sphere will be dominating, and then this projectile will continue. So we have to consider the velocity such that it will reach up to neutral point only, and after that the second sphere's gravitational pull will do the rest. So for that reason, Okay, here we have to apply the conservation of energy as we have done in the expression of escape speed. So what will happen? The energy, total mechanical energy at point A should be equal to the total mechanical energy at point neutral point, means at point N, and this should be equal to the total mechanical energy at point B. So the total mechanical energy at point A will be, look, here we have thrown with velocity v, so there will be kinetic energy 1 by 2 m v square, and then we have minus g into m by r. This is potential energy due to this first sphere, and there is another sphere here. So because of this sphere, there will be potential energy in this mass small m, and this we can write minus g into 4m, capital M is here, into m divided by this distance. So this will be 5r. Okay, so this is the energy at point A, and this should be equal to energy at point N. And energy at point N, we are considering that we have to throw this projectile such that it attains this position. Okay, so here we are taking, let's say here we are taking that this projectile is coming to rest. In this case, the total mechanical energy will be only potential energy. So minus g m into m by, what is the distance from this center? So it is 2r. So we can write here 2r, and then due to this second sphere, g m by, from here to here it will be 4r. So it will be 4r. Okay, now these two energies should be equal. So we can write 1 by 2 m v square minus g m into m by r minus g 4m, capital M is here, into m by 5r equals to minus g m into m by 2r, and yes, this is 4m, I guess, because this is for the second sphere. So minus g 4m into m by 4r. So it will be g m by r, and now we have both sides this thing, so we can just eliminate this thing. So mv square equals to g 4m into m by 5r, and minus g m by 2r, or we can write g m by r outside, and then we will have 4 by 5 here minus 1 by 2 here. So further we can write v square equals to twice g capital M by r. I have just divided by small m both sides. So this will be 4 by 5 and 1 by 2, we can say 10, 8 minus 5, and then we will have 2gm by r, 3 by 10, and ultimately we can write it 3gm by 5r. So v will be 3gm by 5r, the square root of this thing. So this is the minimum speed required to project this projectile from here so that it can reach up to the second sphere surface. Okay, or you can find out what is the speed at this position, means when it reaches the second sphere, what is the speed at point B. So for that you have to just extend this thing. Total mechanical energy at point B will be 1 by 2 m, let's say velocity is there, is v1 or vb more precisely, square minus g into 4m m by r minus g m into m by 5r. Yes, from here to here it is 5r. So this is energy at point B, and you can equate this energy with this, and you can get what will be the speed at point B of this projectile. So this is all for this video.